Hello students, welcome back to my channel. In this video, I am going to discuss in detail about the UV spectroscopy. Generally, UV spectroscopy involves the interaction of the electromagnetic radiation, especially in the UV region, with the matter. So, UV spectroscopy generally involves the interaction of UV radiations with the matter. So, the UV radiations generally extends from 200 to 400 nanometers is much informative than the UV radiations which extends below 200. So whenever the spectrum is drawn below 200 nanometers, then it is difficult to monitor, since even in that region air shows the absorption. So in particular, with respect to UV spectroscopy, the spectrum is drawn in 200 to 400 nanometers. So here, coming to the UV spectroscopy, generally it is measured in terms of wavelength, and the units are nanometers. Here the spectrum is drawn between the wavelength and the absorbance. Generally it is a parabola in the UV region. So UV spectroscopy extends from 200 to 400 nanometers, and always UV spectra is drawn between wavelength and absorbance. So coming to the importance of UV spectroscopy, it gives much information about the conjugated double bonds. UV spectroscopy is also known as electronic spectroscopy. Since whenever the energy is absorbed in the UV region, automatically the electrons will be excited from the ground state to the higher energy levels. So it is responsible for electronic transitions. And hence UV spectroscopy, also called as electronic spectroscopy. Coming to the important applications of UV spectroscopy, here UV spectroscopy generally involves the excitation of sigma, pi and n electrons to sigma star and pi star excited levels. So especially there are four types of electronic transitions which are possible in the UV region, which generally includes sigma to sigma star, n to sigma star, pi to pi star and n to pi star. So let me discuss about the important applications of UV spectroscopy. So coming to the important applications, the UV spectroscopy is highly useful for the detection of conjugated systems. So let us suppose that here we will consider three different compounds, namely ethylene, 1,3-butadiene, and benzene. So whenever the spectrum, especially UV spectrum, is drawn for these three compounds, then the lambda max for these compounds will be absorbed at 170 nanometers, 270 nanometers and 255 nanometers respectively. So ethylene shows a characteristic absorption at 170 nanometers. 1,3-butadiene shows characteristic absorption at 270 nanometers and benzene shows characteristic absorption at 255 nanometers. From these three examples, it is very clear that if a compound contains at least two double bonds in conjugation, then the absorption maximum will be absorbed in the allowed UV region, that is 200 to 400 nanometers. So in order to detect the presence of conjugated system, especially the presence of two double bonds, it is possible in UV region. So if the compound contains at least two double bonds in conjugation, then its presence can be identified in the UV region. Coming to the benzene, it contains three double bonds and hence the absorption maximum is absorbed at 255 nanometers. That means as the number of double bonds in conjugation increases, automatically the absorption maximum will be shifted to the longer wavelength region. At the same time, it is possible to detect the unknown compound by getting the spectrum in the UV region. So let us suppose that when a graph is drawn in the UV region, lambda max is absorbed at 280 nanometers. That means the given compound may be aniline. Since generally the presence of lone pair of electrons on nitrogen will extend the conjugation and hence the absorption maximum will be shifted to higher wavelength region. Similarly, it is possible to detect the impurities present in the given compound, especially whenever if we consider ethanol as the solvent. Ethanol shows no characteristic absorption in 200 to 400 nanometers and hence it can be called as transparent in UV region. So ethanol is transparent in UV region. If at all benzene is present along with the ethanol, then it shows a characteristic absorption at 280 nanometers. So sometimes ethanol may contain benzene as the impurity. In that case, we can observe the characteristic absorption at 280 nanometers. In that way, it is possible to identify the impurities present in the given solvent. With the help of UV spectroscopy, it is possible to identify geometrical isomers. Geometrical isomers means cis-trans isomers. Let us consider one best example, that is stilbene. So whenever if we consider cis-stilbene, it shows characteristic absorption at 280 nanometers, whereas trans-stilbene shows characteristic absorption at 295 nanometers, and the difference in the absorption maximum is due to their structure. Let us consider the structure of cis-stilbene and trans-stilbene. This is the structure of cis-stilbene. Here in the case of cis-stilbene, the two bulky benzene nucleus are present on the same side of the double bond, with the result in order to excite the electrons it requires more energy, and hence the absorption maximum will be observed at lower wavelength region, that is at the shorter wavelength region. So coming to the trans-stilbene, here the two bulky groups are present on the opposite side of the double bond, and hence even at low energy the electrons can be excited, and hence lambda maximum is observed at 295 nanometers. So in that way it is possible to identify cis-trans isomers with the help of drawing a spectrum in UV region. It is also possible to identify the presence of hydrogen bonding in the given solvents. So if at all polar solvent is present, then it is responsible for the solvation, and hence the lambda max will be shifted towards the shorter wavelength region. That means due to the presence of polar solvent, all the molecules will associate, and with the result the energy at the ground level will be decreased, and hence in order to excite the electrons from the ground state to the excited levels, we require more energy. That means the absorption maximum will be observed at the shorter wavelength region. This is all about the UV spectroscopy and its important applications. If you like the video, don't forget to like, share and subscribe. Thanks for watching. Have a nice day.